Magnetic induction is a communication technique that has been employed for many years, notably in applications like communicating with submersible pumps. The fundamental principle involves using a magnetic field to transmit data or signals. This method relies on the creation of a magnetic field by a transmitting device, which induces a current in a receiving device located within a field's range. The induced current is then interpreted as the transmitted information. In the context of submersible pumps, magnetic induction allows for control and monitoring signals to be sent to the pump without requiring a direct physical connection. This is particularly useful in environments where traditional wired communication is impractical or unreliable. Now, regarding the power requirements of magnetic induction versus radio frequency or RF communication, magnetic induction typically demands significantly high power levels to achieve comparable communication distances and data rates. This is due to the nature of magnetic fields, which attenuate more rapidly with distance than radio waves. For instance, to transmit a signal over a distance of several meters using magnetic induction, a substantial amount of power is needed to generate a detectable magnetic field at the receiving end. In contrast, RF communication can achieve the same range with considerably less power thanks to the ability of radio waves to propagate more efficiently through the air. This difference in power efficiency is a critical factor when evaluating the potential risks associated with magnetic induction communication. The potential hazards associated with magnetic fields depend largely on their strength and frequency. Low-frequency magnetic fields, such as those produced by household appliances and power lines, are generally considered to pose minimal health risks, although ongoing research continues to investigate long-term effects. High-frequency magnetic fields, like those used in RF communication, can generate heat in biological tissues if the field strength is sufficiently high. This is the principle behind microwave ovens. The levels of magnetic flux generated by a switch leg in electrical wiring are typically very low and are not considered a significant hazard. A switch leg is simply the portion of an electrical circuit that runs from a switch to the electrical device it controls, such as a light fixture. The current flowing through the switch leg creates a magnetic field, but the field strength is usually weak and localized. Similarly, the magnetic flux from low-power wireless devices, such as wireless mice and keyboards, is also very low. These devices are designed to operate with minimal power consumption to extend battery life. The magnetic fields they produce are well below the levels that would be considered harmful. Now, to consider whether the use of strong magnetic flux for communication poses a hazard, several factors need to be taken into account. Firstly, the strength of the magnetic field is crucial. Higher field strengths are more likely to pose a risk. Secondly, the frequency of the magnetic field is also important, as higher frequencies can cause heating effects. Thirdly, the duration of exposure to the magnetic field is a factor, as prolonged exposure can increase the potential for harm. Finally, the distance from the source of the magnetic field is critical, as the field strength decreases rapidly with distance. Given that the described communication technique involves low-power devices operating over a short range, it is unlikely to pose a significant hazard. The magnetic field strengths involved would likely be well below the levels that are known to cause harm. However, it is always prudent to follow safety guidelines and minimize exposure to electromagnetic fields whenever possible. In summary, magnetic induction is an established communication technique with a history of use in applications like submersible pumps. While it generally requires more power than RF communication, the magnetic fields produced by low-power devices operating over short ranges are unlikely to pose a significant hazard. Nevertheless, it is advisable to be mindful of safety guidelines and minimize exposure to electromagnetic fields. To elaborate further on the technical aspects, let's delve into the specifics of magnetic induction and its applications. Magnetic induction, at its core, is the generation of an electromotive force, or EMF, in a conductor due to a changing magnetic field. This phenomenon is described by Faraday's law of induction, which states that the induced EMF in any closed circuit is equal to the negative of the time rate of change of the magnetic flux through the circuit. Mathematically, this is represented as EMF equals negative d phi divided by dt, where phi is the magnetic flux and t is time. The magnetic flux, in turn, is a measure of the quantity of magnetic field passing through a given area. It is calculated as the integral of the magnetic field strength, B, over the area, A, that is, phi equals the integral of B dot dA. The dot product indicates that only the component of the magnetic field perpendicular to the area contributes to the flux. In the context of communication, magnetic induction is used to transmit information by modulating the magnetic field. This modulation can take various forms such as amplitude modulation, AM, frequency modulation, FM, or phase modulation, PM, depending on the specific application and design. The modulated magnetic field then induces a corresponding signal in a receiving coil, which is demodulated to extract the original information. The efficiency of magnetic induction communication depends on several factors, including the size and shape of the transmitting and receiving coils, the distance between them, the frequency of the magnetic field, and the properties of the surrounding medium. Larger coils in closer proximity generally result in stronger induced signals and better communication performance. Higher frequencies can also improve the data rate, but they also lead to increased losses due to skin effect and other factors. The choice of frequency is therefore a trade-off between data rate and efficiency. Now let's compare magnetic induction with radio frequency, or RF communication, in more detail. RF communication relies on the transmission of electromagnetic waves through the air. These waves consist of oscillating electric and magnetic fields that propagate at the speed of light. The frequency of the electromagnetic waves determines their properties and behavior. Lower frequencies, such as those used in AM radio, can travel long distances and penetrate obstacles more easily, but they have limited bandwidth and data rate. Higher frequencies, such as those used in Wi-Fi and cellular communication, offer much higher bandwidth and data rate, but they have shorter range and are more susceptible to interference. The power required for RF communication depends on several factors, including the frequency, the distance, the antenna gain, and the receiver sensitivity. In general, RF communication is more energy efficient than magnetic induction for long-distance communication, because electromagnetic waves can propagate over long distances with relatively little attenuation. However, magnetic induction can be more efficient for short-distance communication, especially in environments where RF signals are blocked or attenuated by obstacles. One of the key advantages of magnetic induction is that it does not require a direct line of sight between the transmitter and receiver. This makes it suitable for applications where the transmitter and receiver are separated by opaque materials, such as in underwater communication or communication through walls. Another advantage of magnetic induction is that it is less susceptible to interference from other RF sources. This is because magnetic fields are less easily shielded than electromagnetic waves. However, magnetic induction is also more susceptible to interference from metallic objects, which can distort the magnetic field and reduce the signal strength. Turning to the potential hazards associated with magnetic fields, it's essential to understand the difference between static magnetic fields and time-varying magnetic fields. Static magnetic fields, such as those produced by permanent magnets, exert a force on moving charges. This force can be used to levitate objects, deflect charged particles, or generate electricity. However, static magnetic fields are not generally considered to pose a significant health risk unless they are extremely strong. Time-varying magnetic fields, on the other hand, can induce electric currents in conductive materials, including biological tissues. These induced currents can cause various effects depending on the frequency and strength of the magnetic field. At low frequencies, such as those used in power lines, the induced currents are generally too weak to cause any noticeable effects. However, at higher frequencies, such as those used in RF communication, the induced currents can generate heat in the tissues. This is the principle behind microwave ovens, which use high-frequency electromagnetic waves to heat food. The potential for heat generation depends on the specific absorption rate, or SAR, which is a measure of the rate at which energy is absorbed by the body. Regulatory agencies, such as the Federal Communications Commission (FCC) and the International Commission on Non-Ionizing Radiation Protection (ICNIRP), have established limits on SAR to protect the public from the harmful effects of electromagnetic radiation. These limits vary depending on the frequency and the exposure scenario. In the case of low-power wireless devices, such as wireless mice and keyboards, the magnetic field strengths and frequencies are typically very low, and the SAR values are well below the regulatory limits. Therefore, these devices are not considered to pose a significant health risk. However, it is always prudent to follow safety guidelines and minimize exposure to electromagnetic fields whenever possible. Some simple steps that can be taken to reduce exposure include increasing the distance from the source, reducing the duration of exposure, and using shielding materials. To further clarify the specific application mentioned, the use of magnetic induction for communication over a few meters, it is important to consider the practical limitations and advantages in that scenario. Over such a short distance, the higher power requirement of magnetic induction compared to RF becomes less of a disadvantage. The key benefit here lies in the potential for more reliable communication in environments where RF signals might be obstructed or experience significant interference. For example, in industrial settings with heavy machinery or dense metallic structures, magnetic induction could offer a more robust communication link than wireless protocols like Bluetooth or Wi-Fi, which rely on radio waves. The effectiveness of magnetic induction in this context hinges on careful design of the transmitting and receiving coils, optimizing their size, shape, and orientation to maximize the magnetic flux linkage. The choice of operating frequency is also critical, balancing the need for sufficient bandwidth to support the desired data rate with the constraints imposed by coil impedance and losses. Furthermore, signal processing techniques can be employed to mitigate noise and interference, improving the overall reliability of the communication link. From a safety perspective, the magnetic field strengths involved in such short range, low power applications are unlikely to pose a significant hazard. However, it's still important to ensure compliance with relevant safety standards and guidelines, particularly regarding limits on magnetic field exposure. The potential for interference with other electronic devices should also be considered, although this is generally less of a concern at these low power levels. In summary, while magnetic induction may not be the most energy-efficient communication method for long distances, it can offer a viable and reliable alternative for short-range applications in challenging environments. The key is to carefully design the system and ensure compliance with safety regulations. Thinking about the long-term implications, the advancement in materials science has led to the creation of materials that can manipulate magnetic fields in unique ways. Metamaterials, for example, are artificially engineered materials that exhibit electromagnetic properties not found in nature. These materials can be designed to focus, guide, or even cloak magnetic fields, potentially enabling new and improved magnetic induction communication systems. For instance, metamaterials could be used to enhance the coupling between transmitting and receiving coils, increasing the communication range and efficiency. They could also be used to shield sensitive electronic devices from external magnetic fields, reducing interference and improving performance. Furthermore, the development of new magnetic sensors and actuators could lead to more sophisticated and versatile magnetic induction communication systems. These sensors could be used to detect weak magnetic fields with high precision, while these actuators could be used to generate strong magnetic fields with minimal power consumption. As technology evolves, the potential applications of magnetic induction communication are likely to expand beyond traditional areas such as submersible pumps and short-range wireless links. We may see it used in new and innovative ways, such as in implantable medical devices, wireless power transfer systems, and even in new forms of human-computer interaction. As with any emerging technology, it's important to carefully assess the potential risks and benefits before widespread adoption. Thorough research and testing are needed to ensure that magnetic induction communication systems are safe, reliable, and environmentally sound. This includes investigating the potential for interference with other electronic devices, the long-term health effects of exposure to magnetic fields, and the environmental impact of manufacturing and disposing of magnetic materials. By taking a proactive and responsible approach, we can harness the full potential of magnetic induction communication while minimizing the risks. Finally, let's address the specific concern about magnetic flux from a switch leg without a neutral run. In a typical alternating current, or AC circuit, the current flows in both directions, creating a magnetic field that alternates in polarity. When the current flows through a conductor, such as a wire in a switch leg, it generates a magnetic field around the conductor. The strength of the magnetic field is proportional to the current flowing through the conductor. In a balanced AC circuit, the current flowing in the hot wire is equal to the current flowing in the neutral wire, and the magnetic fields produced by the two wires cancel each other out. However, in a switch leg without a neutral run, the current only flows through the hot wire when the switch is closed, and there is no corresponding current in the neutral wire to cancel out the magnetic field. This can result in a net magnetic field around the switch leg. The strength of this magnetic field is typically very low, especially in residential wiring, and it is not considered a significant hazard. However, some people may be concerned about the potential health effects of exposure to even low levels of magnetic fields. The scientific evidence on this topic is mixed, and there is no conclusive proof that exposure to low-level magnetic fields causes harm. Nevertheless, it is always prudent to minimize exposure to electromagnetic fields whenever possible. One way to reduce the magnetic field around a switch leg is to run the hot and neutral wires together so that their magnetic fields cancel each other out. This is typically done in modern electrical wiring. Another way to reduce the magnetic field is to use shielded cables, which contain a layer of conductive material that blocks electromagnetic fields. In summary, while the magnetic flux from a switch leg without a neutral run may be a concern for some people, it is typically very low and is not considered a significant hazard. However, it is always prudent to minimize exposure to electromagnetic fields whenever possible, and there are several steps that can be taken to reduce the magnetic field around a switch leg.